Wow, don't be afraid to clap or cheer. Today is a celebration. And what you just witnessed was a glimpse of years of hard work and dedication from a devoted and collaborative team. They dared to pull off what some would call seemingly impossible, to gather our largest asteroid sample ever and bring it home safely to Earth. I'm Shaniqua Vereen with NASA's Office of Communications, and I will be your host today as we bring you to the heart of the Johnson Space Center's Curation Lab, introduce you to some of the team members hard at work, and provide you with a first look at our initial findings. Thank you all for being here, and welcome to the much anticipated OSIRIS-REx sample reveal. All right, we'll kick things off, and we'll start with a proper Houston welcome. I'm pleased to introduce to you Vanessa Weich, Director of the Johnson Space Center.
Thank you, Shaniqua. Good morning, and welcome to NASA's Johnson Space Center. We're here today for a very exciting moment in history, the sample reveal of OSIRIS-REx. The Johnson Space Center has played a pivotal role in many firsts in human spaceflight, from landing the first person on the moon to supporting NASA astronaut Frank Rubio's recent record-breaking 371 days in space on the International Space Station. We can clap for that. And now, NASA's first mission to deliver the largest sample collected from an asteroid to Earth. We are the hub of human space exploration, home to America's Astronaut Corps, mission operations at the Johnson Space Center. Our workforce also includes the world's leading sample scientists, and we curate the most extensive collection of extraterrestrial materials on Earth. We're honored to be joined by some special guests today. Please help me in welcoming NASA leadership, Administrator Bill Nelson, Director of Goddard Space Flight Center, Mackenzie Lystrup, and Director of the Planetary Science Division in NASA's Science Mission Directorate, Lori Glaze. They'll be out soon. Sharing scientific data with the world, our curation lab will distribute fractions of the asteroid Bennu sample to a sample analysis team of more than 200 members from more than 35 globally distributed institutions. We're pleased to be joined by the international community with representatives from Japan Aerospace Exploration Agency and the Canadian Space Agency, who will both curate a portion of the sample for analysis. As we venture to explore to deep space, our collaborative international partnerships will bolster space exploration and enhance peaceful relationships between our nations. We do have a lot of exciting work here at the Johnson Space Center with the intention to inspire the next generation of explorers, the Artemis generation, represented today by Houston Independent School District. Where are you guys? And the San Antonio Independent School Districts. The sample that we're going to have today will unlock new insights into the origins of our solar system and help answer ancient questions about our own planet. And a large fraction will be stored and available for future generations of scientists, and that could be one of you. I would like to also recognize we have representation here from the offices of Senator Cruz, Representative Jackson Lee, Representative Brian Babbins, Representative Weber, Representative Garcia, Representative Fletcher, also from the Office of State Senator Middleton and State Representative Bonin. And we thank them for their bipartisan support. Thank you all for being with us to witness history in the making. OSIRIS-REx embarked on a 7-year journey to Bennu and back to bring us this sample. In fact, the mission was selected in 2011, so this historic day has been in the making for 12 years. Can we get a round of applause in celebration of the researchers at the University of Arizona Lunar and Planetary Laboratory, Lockheed Martin, Jacobs, the NASA workforce, and all those across the agency who came together to make this very exciting moment in history happen. Let's give them a round of applause. Thank you, thank you. I hope all of you are as excited about this mission as I am. It will help scientists investigate our planet's formation and for us all to experience our next giant leap together. Thank you.
Thank you, Director Weich. A mission like OSIRIS-REx is bigger than one person, one agency, or even one nation. It takes the careful work and collaboration of hundreds of engineers, scientists, mission managers, and more. Our next guest leads the NASA Center that oversaw the mission management systems engineering, safety mission assurance for OSIRIS-REx. I am pleased to introduce the Director of Goddard Space Flight Center, Dr. Mackenzie Lystrup.
Hello, everyone, and thank you, Shaniqua, and thank you, Vanessa, for hosting us here today. This is an exciting example of NASA, one NASA center passing the baton to another, and is really NASA at its best and most collaborative. You know, this mission exemplifies that collaboration is what leads us into a new era of exploration. And this is the era of sample science. This is when sample science really begins. OSIRIS-REx took aim at some of the biggest questions in exploration and science. You know, how did our solar system form, and how did life originate on Earth? It can't get more exciting than that. We can't answer these kinds of science questions without fantastic engineering, and I'm really proud of the team at Goddard, at Lockheed Martin, and at the University of Arizona that oversaw the mission for more than a decade. It's really scientists and engineers coming together in order to make our scientific dreams come true. It was exciting to be in Utah just a few weeks ago and seeing the moment that the capsule hit the desert floor after 7 years in space. It was an exciting moment to see, but really the real journey begins now. It's worth remembering that this team accomplished almost the impossible here, and we were able to, from the maybe back of the envelope science ideas of what OSIRIS-REx could possibly do, all the way through to conceptualizing this amazing mission, building it, testing it, launching it, going to the asteroid, taking the sample, coming back to Earth, landing in Utah, and now here at home at Johnson Space Center. This is the smallest body we've ever orbited before. At one point, it was orbiting only a radius of 0.6 of a mile. I mean, that's just walking distance. So it's really a brand new era for us at NASA, and it's the first time that the United States has brought a sample back from space and landed it safely on Earth. We've been able to map the entire surface of Bennu in detail to find the safest and best landing site, and it's really helped us understand these kinds of asteroids in more detail. But now, of course, we are going to be looking in detail for the first time at these samples. So we're at the point where we have justified all of the really hard work. And again, we're handing the baton off to the really world-class sample facility here at Johnson Space Center. So I want to give a round of applause to Johnson here. So you hear today that our scientists are incredibly eager to get at the samples. I know that there are Goddard scientists as well who are waiting for their small piece of the sample. So over the next months and years, we're all going to be definitely rewriting some history. When we do, I want all of the team members and their families to really recognize that the revelations that we're going to make here are standing on the shoulders of the incredible engineering and science that you've all delivered. Thank you and enjoy today.
Thank you, Dr. Leidstra. Johnson Space Center is best known as the home to the Astronaut Corps and NASA's Human Spaceflight Program. It's also home to the Astromaterials Research and Exploration Science Division, or ARES. Its mission is to combine scientific and engineering expertise in order to advance human space exploration, to integrate terrestrial and planetary research, and to promote successful space missions by mitigating risk. NASA has the world's leading sample scientists and creates the most extensive collection of extraterrestrial materials on Earth, which includes lunar samples from our Apollo missions, cosmic dust, solar wind particles, meteorites, microparticle impacts, the JAXA-led Hayabusa and Hayabusa 2 asteroid samples, and now OSIRIS-REx and the samples we collected from asteroid Bennu. Our team has been caring for the OSIRIS-REx sample and its contents since it arrived in Houston on September 25th. Now let's hear from a crucial member of the team. Please join me in welcoming Dr. Eileen Stansberry, Chief Scientist at NASA's Johnson Space Center.
Thank you. I'm honored to be here celebrating with you all today and representing science at JSC. This sample return mission is an important part of an integrated planetary exploration strategy answering fundamental questions on the formation and evolution of our solar system. The pristine sample material from Bennu represents a valuable resource providing a window into the early solar system and is the newest addition to NASA's astromaterials collections. Our role in astromaterials curation is to catalog and safely contain received samples. The process for deintegration and curation for OSIRIS-REx has been thoroughly planned and practiced with the mission science team. Opening the science canister and methodically removing tag SAM revealed an abundance of sample from asteroid Bennu, and even though the tag SAM head is not yet open. With this abundance, we're taking our time methodically processing to properly care for every valuable piece of Bennu. And with the overflow of sample found on the avionics deck spilling out of the tag SAM, we have plenty to show you today. The science obtained during the mission so far, coupled with the samples we're only now getting a glimpse of, are just the beginning of the wealth of knowledge that we can expect from OSIRIS-REx. Sample return missions are unique. They provide for large sample science return using advanced instrumentation that you cannot fly on a spacecraft. Analysis is not limited by the ideas formed years ago when the missions were first conceived, and measurements can be made and cross-compared using different techniques to resolve unexpected or ambiguous results. The samples are then available for new questions, new techniques, new instrumentation far into the future, and they are the gift that keeps on giving. I'm proud of the stewardship that we commit to these samples as we begin this next phase of the mission with sample curation and scientific analysis, celebrating the legacy that the OSIRIS-REx mission is providing to current and future generations of scientists. Let's take a look at the people and labs that are working with our newest astromaterials, the OSIRIS-REx samples of Bennu.
The OSIRIS-REx mission was a spacecraft that launched in 2016 to collect asteroid samples from the carbonaceous asteroid Bennu.
And a carbonaceous asteroid means it's a likely storage for prebiotic compounds, so organic compounds that could have been the building blocks for life on Earth and potentially other places in our solar system.
And some of these samples may even have remnants from before the solar system, pre-solar grains that allow us to study the raw material that made ours and other planets.
With us bringing this particular asteroid back, this is some of the most pristine material of asteroid sample that we have in our current collections.
The Astromaterials Research and Exploration Science Division, or the ARES division, is a division within NASA that focuses on the study and preservation of rocks from space.
This is a group of a really diverse range of scientists and engineers that are exploring our solar system through studying samples, developing things like lunar simulants, being part of NASA missions that range from the exploration of Mars, including the Curiosity and Perseverance rover, supporting the Artemis missions, as well as OSIRIS-REx.
We have meteorites that fall into Earth. They are altered by the Earth's atmosphere. They have been exposed to Earth's chemical compositions. They are contaminated samples.
And in our curation labs, we carefully work on samples in clean rooms, nitrogen atmospheric glove boxes that protect the samples from Earth's atmosphere, oxygen and humidity.
You don't want to study us on samples. You want to study the actual samples in its original state. And so pristinity within curation is very important, and we go to great lengths to make that happen.
Every time we do that kind of probing investigation, we learn something new about the nature of the universe and ourselves.
3, 2, 1.
I feel like humans, since the beginning of time, have always been explorers. We have not stayed in one place. We have ventured out to various continents, and eventually that was going to happen with planets or asteroid bodies.
Whether it's Artemis or Mars, everything we've learned on OSIRIS-REx is going to further our knowledge and our technology development for the next set of missions that we have coming up.
These samples are here on Earth for future generations. 50 years from now, we can be studying these with instruments we couldn't have imagined before. So I think that's one of the most important aspects of this mission, is bringing the samples back. We've waited for 7 years, and now we can reveal what's inside.
Next up is someone who needs little introduction. He leads our agency and keeps a close eye on our efforts across the solar system. Please join me in welcoming NASA Administrator, Senator Bill Nelson.
Hey everybody, it's days like this that continue to amaze me. And what we do in this little agency, it's all amazing. I'm going back to the Cape this afternoon because we're launching a $1 billion spacecraft all the way beyond Mars, closer to Jupiter. And it's going to snuggle up next to a metallic asteroid. And we're going to learn something about that metallic asteroid. I hope we might find diamonds and rubies on that asteroid. But it's a reflection of our country, our can-do spirit. America is defined by possibilities. And we've always been a nation that is restless unless we're pressing the unknown. For 65 years of NASA's existence, and this is our birthday, NASA has responded to America's call. And the story of this little agency is the story of technologies transformed, of barriers broken, of making the impossible possible. And so through missions like what will be Psyche, the one lifting off tomorrow, or Perseverance, the rover that is running around on Mars and digging samples in our search for life there, or the little helicopter that's now flown upwards of 60 times. We just wanted to see if a helicopter could fly in a 1% atmosphere. It's flown 60 times. If it's the James Webb Space Telescope, look at the discoveries. We are going to have answers to questions that we don't even know what the questions are now. Everything is a new discovery as we are glimpsing the early part of the development of this magnificent thing called the universe. And now, OSIRIS-REx. And it's giving us a glimpse into what lies beyond. So 7 years, almost 4 billion miles of a journey throughout the solar system to the asteroid Bennu, now back, and OSIRIS-REx, the sample return capsule, landed in Utah. Right on the money. It was a picture-perfect mission. It's a feat of engineering, and it's NASA's first ever sample from an asteroid. So, you ready to see the results of the mission? Take a peek. So the first analysis shows samples that contain abundant water in the form of hydrated clay minerals, and they contain carbon, and you could see the carbon there, as both minerals and organic molecules. And at nearly 5% carbon by weight, carbon being the central element of life, a far exceeding our goal of 60 grams. This is the biggest carbon-rich asteroid sample ever returned to Earth. Carbon and water are molecules. The carbon and water molecules are exactly the kinds of material that we wanted to find. They are crucial elements in the formation of our own planet. And they're going to help us determine the origin of elements that could have led to life. And I mentioned that one of our missions, it's actually in statute, is to look for life. That's why we're digging on Mars. That's why we go out into the far regions of the very beginning, capturing light from the formation of the first galaxies with James Webb. Now we're looking at this, and what you're seeing today, there's so much more to learn, and there's so much more now that we have this sample to analyze. And why are we doing this? Because at NASA, we are trying to find out who we are, what we are, where we came from, what is our place in this vastness called the universe. And this mission will help our scientists investigate planet formation for generations to come. And it's going to deepen our understanding of our solar system. And it's going to improve our understanding of asteroids that could threaten us here on Earth, helping us protect our planet. And oh, by the way, do you remember DART? We intercepted it at 7 million miles away, and it was bullseye. And we moved the trajectory of that asteroid. So this sample return is proof, again, that NASA does big things, things that inspire us and unite us. NASA brings us together in unity. And things that show that nothing is beyond our reach when we work together. So now I want to take you to the curation lab here at JSC, where a team of scientists are hard at work since the sample arrived just 2 weeks ago.
Thank you, Administrator Nelson. Now, I know you're all ready to learn more about this sample, and I am here with someone who can make that all happen. I am joined today by NASA's OSIRIS-REx curation lead, Dr. Nicole Lunning, and we are standing just outside of the OSIRIS-REx pristine curation clean room. Nicole, before we get started, can you tell us a little bit more about where we're standing right now?
Yeah, thank you, Courtney. So we're in front of the newest curation lab in Historic Building 31, which is home to the largest collection of astromaterials in the world.
Now, the world just got its first look at this gorgeous sample. Can you tell us about how the curation process has been going so far?
Yeah, it's been incredible so far. On Sunday, September 24th, the sample return capsule landed safely in Utah, and then it was brought to a temporary clean room that we had set up there to have certain parts removed, specifically the heat shield and back shell, which are two large parts, and that exposed the sample canister inside, which a nitrogen flow or purge was attached to protect the sample. And then with that nitrogen flow attached, the next day, Monday, September 25th, it was flown from Utah to Ellington Air Force Base and brought here to Building 31 where we are now. And it was safely brought into one of our large glove boxes behind us that first day. The next day, our team was able to remove the canister lid, and that gave us our first glimpse of the TAGSAM head, but also a surprise in that there was sample outside of the TAGSAM head within that sample canister. That was kind of an extra or bonus sample for us.
Well, what an honor to be standing right here, so close to the sample with you today. So you mentioned that bonus sample. What have the initial findings been for the curation team?
Yeah, it's a combination of fine dust as well as some what we call intermediate sized particles, particles that are roughly the size of the short width of a grain of rice, which we've carefully collected and also have already allocated some to the science team, the sample analysis team, which you'll hear a little bit more about from Dante and Danny in the quick look analyses.
And of course, this is not just a NASA mission. There have been several partners along the way. Can you tell us a little bit more about how many scientists are working on this?
Yeah, so we have two incredible international partners, JAXA and CSA, and also the sample analysis team includes over 230 scientists from around the world who will really intensely work on studying some of the sample for the next 2 years. We'll also have 3 samples go to museums in the next couple months. So folks at home may have the opportunity to go and see the sample themselves at the Smithsonian in Washington, D.C., the University of Arizona Museum in Tucson, or at Space Center Houston right here in Texas.
So exciting. So what does it mean for your team to have seen this clean room built from the ground up and now to see the sample in it? I'm sure it has to be so exciting.
Oh, it's incredible. So this clean room was constructed very specifically for the OSIRIS-REx sample, since the scientific goals of this mission are really tied to the building blocks of life and organics. Organic contamination was a really detailed concern to us throughout the entire design and construction process and outfitting. So everything you see in this lab was carefully reviewed to make sure it wouldn't contaminate the sample so we can get the most scientific benefit out of this return.
So can you tell us a little bit about how long it will take to fully reveal the sample and where the sample will live?
Yeah, so the sample's permanent home is this lab behind us. But what will actually happen next is we'll continue taking the TAGSAM apart. So right now we have this incredible view of the sample into the TAGSAM. We're looking into the part that touched the asteroid Bennu. We're actually going to take those parts off to get a little further in so that we can then distribute that sample into bulk sample handling trays, which are triangular and look sort of like deep dish pizzas.
And for scientists interested, how will they eventually be able to request a sample?
So in about 6 months, we will release a sample catalog which will give scientists from all around, even beyond the sample analysis team, enough information to start to think about what science questions they want to ask, and they can propose studies and specific quantities of sample they would like to use. And then those requests will be reviewed by a peer review allocation board. And then those who are granted their requests will get samples in the next 9 months or so.
All right, well, Nicole, thank you so much for joining us today. And as you can see, we are just beginning this process here at Johnson Space Center, but there is much more work to do. So we'll send it back to the auditorium for now.
After its 7-year journey, it's amazing to finally see a glimpse of the samples that were captured from asteroid Bennu. Not only will this mission help us dive deeper into how planets formed and how life began, it also will allow for current and future scientists to make discoveries for years to come. Now, to help us take a closer look into what we've learned so far, we have a panel of individuals who played key roles in the OSIRIS-REx mission. Please welcome back NASA Administrator Bill Nelson, OSIRIS-REx Principal Investigator Professor Dante Loretta, OSIRIS-REx Astro Materials Curator Dr. Francis McCubbin, Goddard Space Flight Center Sample Analyst Dr. Daniel Glavin, and Director of the Planetary Science Division Dr. Lori Glaze. I know you all have a lot to say, so let's get started. Administrator Nelson, let's start with you.
Well, this is an example of why we do make the impossible possible. It's a team that no matter where we are, we all work together. You all know Pam Melroy and Bob Cabana, and we, the three of us, operate as a crew. It's because of that unity, that relationship, that watching each other's back, that we get so much done. And here is another example of what you've seen today. Now, I want you all to hear from the real experts. So take it away, panel.
Thank you, Administrator Nelson. Next up, we have Dr. Francis McCubbin, Astro Materials Curator.
Thanks, everyone. So we are thrilled to have the OSIRIS-REx sample collection here at NASA's Johnson Space Center. And we look forward to the exciting discoveries that are going to be made by the science team with those samples. Over the next 6 months, the curation team and the science team are going to be working closely together to develop a sample catalog that, once released, will provide an opportunity for scientists around the world to request material to study Bennu in their own labs. For now, the curation team is hard at work, carefully and meticulously disassembling the hardware, containerizing asteroid material, and documenting everything they do every step of the way. All of this work takes place inside of a glove box. And those glove boxes are necessary to keep these samples as pristine as the day that the sample landed in Utah. Now, as you've heard, we have a bounty of sample on our hands already, and we're not even inside of TAGSAM. The views here are amazing of this sample, and they're only going to get better. Now, as you can imagine, working with hands inside of a glove box within a clean lab is hard, challenging work, and it does not go quickly. But we need to do this right. And in fact, we have a lot of heritage of this working really well to keep samples pristine over multi-decadal timescales. If we just look at our Apollo collection, the samples that were returned in the late 60s and early 70s when humans first went to the moon, to this day, we still get hundreds of sample requests and allocate hundreds of samples to answer questions that we didn't even think to ask at the time that those samples were returned. This is the true value of sample return and of curation and keeping these samples pristine. It allows us to answer questions that would not be possible with the technology of the time. In fact, like all of our astromaterials collections, the OSIRIS-REx collection is going to be conserved so that scientists that aren't even born yet are going to have the opportunity to answer questions about our universe with these samples using technology that has not even been invented. This is the legacy of OSIRIS-REx, end of sample return broadly. And now let's hear some of those science results from the science team.
Thank you, Francis. Next up. Great job, Francis. Next up, we have Professor Dante Loretta, the principal investigator for the OSIRIS-REx program.
All right, thank you, Shaniqua, and thank you, Administrator Nelson, and to Dr. McCubbin. I just want to start out by saying what an honor it is to be on stage here talking about the amazing results. And I want to talk to the young people in the audience, because NASA for me, when I was a kid, was always like a guiding light, like a dream. To work for NASA meant to be part of the best, to be at the forefront of human exploration. And to see this dream coming true today is beyond words for me. So let's start out with taking a look at what we've gotten into so far. As Francis said, it's been going slow and meticulous, but the science is already starting. So if we could bring up my first graphic. So what you're seeing here on the left side is the first look at the tag SAM. So you've got the science canister, that's like the vault that protected the sample on the return journey home. And sitting inside there is the tag SAM. That's the device that actually touched the surface of Bennu, collected sample, kind of like a vacuum cleaner, except in reverse, because we were in space with no air. We brought our own air and pushed that material inside. It's basically like an air filter. And the first thing we noticed was that there was black dust and particles all around the outer edge where the seal had laid down and protected that precious material. And the reason it got pushed out was because we had under that nitrogen purge to keep it, the Earth's atmosphere away from it, and it pushed all the dust and particles to the edge of the canister. And I drew a little white rectangle there on the deck, and that's zoomed in on the image on the right there. And already this is scientific treasure. We see dust particles and we see millimeter particles, which are like a 1/16 of an inch or so in size. And we swept some of that material and we got it to the sample analysis, what I called my Tiger team. They were here at Johnson Space Center. The electron microscopes were fired up and ready. All the other instruments were ready to go, and we got those particles in on the third day that we had the sample here in Houston on September 27th. So let's take a look at some of the first results that we got from those particles. And boy, did we really nail it. So here I'm just showing you 4 different examples. This is taken with an electron microscope. Electrons kind of behave like light waves, but they have much shorter wavelengths, so you can see very, very fine details that you would never be able to see with an optical microscope. The first panel there in the upper left, those are the water-bearing clay minerals, and they have this fibrous kind of structure. We call this serpentine because they look like serpents or snakes inside the sample. And they have water locked inside their crystal structure. And I want to stop and think about what that means. That water, that is how we think water got to the Earth. The reason that Earth is a habitable world, that we have oceans and lakes and rivers and rain, is because these clay minerals like the ones we're seeing from Bennu, landed on Earth 4 billion years ago to 4.5 billion years ago, making our world habitable. So we're seeing the way that water got incorporated into solid material and then ultimately into planets. And not just Earth, but probably Venus and Mars also had abundant water as well. The next one on the upper right, you can see the hexagon. It's got that really like stop sign kind of shape, and that's characteristic of a sulfide mineral. If we could go back, yes, thank you. And sulfur is also a critical element for planetary evolution. It determines how quickly things melt, and it's also critical for biology. A lot of the amino acids that give structure to our proteins use sulfur to link and provide those bridges. And then the bottom 2 there are iron oxide minerals called magnetite, or you might know them as a lodestone. They react to the magnetic fields. The one on the lower left is framboidal, like a raspberry, and the one on the right are plate-like, and especially those platey ones might be really important for organic evolution. They might catalyze certain reactions. So we're looking at the kinds of minerals that may have played essential roles in the origin of life on Earth. Now we can go to the next graphic. One of the coolest techniques that we have here at Johnson Space Center is X-ray computed tomography. It's like a CAT scan. So without cutting into the rock, we can actually look inside. We can see the textures and the distributions of the minerals. This helps us intelligently select areas where we want to make cuts so that we get the most exciting science results. It also gives us a good sense of the size and shape of the particle. This is the biggest one. It's about 2 millimeters across. And you can see here in red those sulfide minerals. I'm particularly fond of those. I'm an expert in sulfide mineralogy, and I can't wait to get inside and look in great detail at what's going on here. And now let's go to the last graphic. We saw Administrator Nelson show you this. I just want to point out a couple of my favorite features. Trust me, I spent the weekend staring at this image for hours and hours and getting more excited by the day. I've got 4 different focus boxes. Let's take a look at B. I call this one of the troublemakers. If you know the story of OSIRIS-REx, you know just a couple days after we collected the sample, we saw material spewing out into outer space, one of the many heart-pounding moments on this mission for me. It's because these large particles got trapped in between this flap, which was designed to keep the precious sample inside. And that's generally good news, right? Because those are big particles, and there's a lot of science to be done there. In panel C, we're just looking at some of the finer grain material, and I'm particularly interested in the different reflectance. Bennu has a salt and pepper kind of texture, bright grains and dark grains, and we're seeing that. In fact, as I was zooming around these images, I felt like I was miniaturized and running around on a tiny little Bennu. Panel D there is one of the really friable looking particles. It's got this kind of hummocky texture. It looks like the dark, large boulders that dominate the surface of the asteroid. And what gets me is the similar size or the similar shapes and textures even as we go to these smaller sizes. Bennu seems to have this kind of fractal nature. And then finally, the last panel there, panel E, just shows 2 very different kinds of rocks sitting next to each other. One of our key hypotheses is that there's 2 major different kinds of rocks on the surface of the asteroid, darker and brighter, weaker and stronger, and we may see those already represented. And just recall, this is the material that leaked out of the tag SEM when we flipped it over. Underneath that flap, there's a whole treasure chest of extraterrestrial material, and trust me, the sample science team can't wait to get their hands on it.
Thank you, Dr. Loretta. Now let's hear from Dr. Daniel Glavin, OSIRIS-REx sample analyst.
Okay, thank you. So we've heard a lot of exciting stuff already about the water and how Bennu could possibly contribute to our oceans. I'm here to talk about carbon. Why is carbon so important? Well, carbon is essential for all life on Earth. We are all carbon-based. Carbon forms bonds with hydrogen, oxygen, nitrogen, and the sulfur to form prebiotic and biological compounds that are important, amino acids that are part of our proteins and enzymes. We even look for nucleobases, components of the genetic code in DNA and RNA. So exciting stuff. And one of the reasons we want to look for this material in these samples is to understand whether asteroids like Bennu could have not only delivered the water that led to our oceans, but actually seed the Earth with prebiotic chemicals, right? The building blocks of life. And this is the part I just find really exciting. So let's get right to it. The first carbon measurement was made at the Carnegie Institution for Science. We heard it from NASA Administrator, about 5%. The actual number is 4.7%, close to 5%. And this was a big deal. At the time this data came back, I mean, there were scientists on the team going, wow, oh my God. And when they say that, scientist says that, wow, that's a big deal. So we were excited right away. In fact, Carnegie said this for the extraterrestrial samples they've analyzed, this is the highest abundance of carbon they've ever measured in any extraterrestrial sample. And they've analyzed close to 250 meteorites. So this is a unique sample that we're dealing with. The second measurement we made, we started to look more at what is the nature of this carbon. You're looking at an image here. Oh my gosh, this was taken in the optical microscopy lab right here at Johnson Space Center. Gorgeous image of a particle of Bennu. On the left, you see a small grain of Bennu in reflected light, visible light, like you'd see with your eye, but magnified. And on the right, you see the same grain, but under UV ultraviolet light. So this is like the crime scene investigation TV show where they go in with the black light and they look for the evidence that they can't see with their naked eye. We're doing the same thing here now, but with a 4.5 billion year old grain from the early solar system. And the stuff's lighting up. You see carbon there in the center, just to the right, the kind of a light bluish fluorescence. That's from a carbonate mineral, so carbon locked up in this mineral grain. But then you see these small specks of light, looks like stars, right, glowing. This is organic matter. Call these organic globules. And I know the analyst at the time who made this measurement said, you know, this thing's loaded with organics. I mean, again, just, you know, this is incredible material. Still a lot of work to do, and we're just beginning here. We're just literally scratching the surface of what's in this material. But we'll be looking for these, again, biologically essential organic molecules over the next month as these samples will go out to labs around the world to study this in more detail. And I want to make just kind of one final point. We've heard about these great initial preliminary results. I know there's more to come. But OSIRIS-REx, the team, we picked the right asteroid. And not only that, we brought back the right sample, right? This stuff is an astrobiologist's dream, you know? Just can't wait to get at it. And this material will be around for generations and generations. We're going to learn so much about the origin of the solar system, the evolution, and potentially how even life started here on Earth.
Thank you, Dr. Glavin. Next up, and finally, we'll hear from Dr. Lori Glaze, Planetary Science Division Director.
Thank you, Shaniqua. It's such an honor to be here today, and what an incredible honor to share the stage with these amazing scientists up here. We're just, within NASA, we're so proud of everything that is gone on so far with this mission. We're so excited for everything yet to come. But I want to note, just beyond the folks that are here, the folks that you saw working in the lab, there's a whole team that's been spending incredible hours over the last 2 weeks to bring you the information that you saw today and to make these early discoveries. It's just an incredible team. They're working really hard, and we keep telling them, don't, take your time, go slow, but they're doing an amazing job. It's really incredible. But as you heard, what you're seeing here today, as exciting as this is really just the beginning. There is so much incredible work to happen. We're going to get that tag SAM opened up. We're going to get the full sample. We'll really get a full picture of what we collected and begin those amazing discoveries. But let me put OSIRIS-REx in a little bit of context about some of the other planetary work that we're doing at NASA. So within our NASA planetary program, we actually have almost 40 missions that are exploring the solar system. Some of those are being developed, some of those are in operations. But within those almost 40 missions, we actually have 7 of those missions that are focused on understanding asteroids. And you heard from Dante about how important asteroids are for understanding the early formation of our solar system, the origin of life and water on Earth, and perhaps other places in the solar system. These asteroids are really, each one of them in different parts of the solar system can give us different pieces of the puzzle about where we came from. And of those 7 missions, right now, we're really lucky because we're in the middle of what we're calling asteroid autumn. We've got several big milestones happening right now on 4 of those missions. Of course, we got the OSIRIS-REx sample that landed on September 24th. Right after, 20 minutes after the entry system was released from the spacecraft, we actually transitioned that spacecraft for a new mission. It's now called OSIRIS-APEX, and that's a mission to go explore the Apophis asteroid. We're actually going to rendezvous with Apophis in 2029, so they've got another long journey and another great goal for that spacecraft. And then 2 days after the OSIRIS-REx samples landed in Utah, we celebrated the 1-year anniversary of the double asteroid redirection test. And you heard Senator Nelson at the beginning mention that. What an incredible feat that was. The first time ever for humanity to change the orbit of a celestial body. And the first time we've demonstrated our ability to protect ourselves from a potentially hazardous asteroid in the future. So now we're celebrating OSIRIS-REx here today, the sample reveal. And then coming up in November 1st, we have another mission that's going to explore a special set of asteroids that are even much further out in the solar system. They lead and trail Jupiter in its orbit around the sun, and those are called Trojan asteroids. That mission, called Lucy, is actually on November 1st going to fly by a main belt asteroid on its way out towards the Jupiter system. And it's going to fly by a main belt asteroid called Dinkinesh, and it's going to allow them to test out all of their operations as they fly by the asteroid. And then finally, the big one that Administrator Nelson also mentioned is that we have a mission called Psyche going to visit a unique asteroid, one of only 9 out of several million asteroids that we believe are out there. There's only about 9 or so that we've discovered so far that we think are really enriched in metal, iron and nickel. And so the Psyche mission is going to go visit that asteroid, 16 Psyche, and we hope to launch it tomorrow. In fact, I'm getting on a plane this afternoon to go back to Florida to hopefully wish it off the surface of Earth tomorrow, but we've got so many opportunities for that to happen. And so that's the next big thing. Pay attention for that one. And with that, I'm going to hand it back to Shaniqua.
Thank you. Thank you, panelists.